Hello, everyone. I'm Liehuang Chen from Tsinghua University. On behalf of the authors, I'm here to present the paper Transferability of White Box Perturbations, Query-Efficient Adversarial Attacks Against Commercial DNN Services. We know deep neural networks, or DNNs, have been widely used in many fields and can solve various tasks, ranging from face recognition to autonomous driving. Many companies like Amazon and Microsoft have also launched cloud-based DNN services. While this has promoted the application of DNN, it has also concentrated the associated risk. That is, a single successful attack could put a large number of devices at risk. Among the attacks on DNNs, the adversarial attack is a method of attacking DNNs by adding subtle perturbations to input images so that the target model would make incorrect decisions. However, commercial DNN services impose additional requirements on attackers targeting adversarial attacks. Since these services often offer APIs to access model input and output, so the attackers can only search for adversarial examples in a black box manner. This also imposes stricter requirements on the query efficiency of the attack. The existing decision-based adversarial attacks mainly fall into three categories: the transfer-based and the query-based, also the hybrid ones. Transfer-based attacks utilize white box attacks against substituted model to craft adversarial perturbations. However, practical scenarios often introduce bias between the target model and the substitute model, which can usually result in a failure to deceive the target model, so the low attack success rate. And query-based attacks start from two images with different labels and gradually reducing their difference through a loop of queries. Though effective, these attacks demand a substantial number of queries to minimize the perturbation. The hybrid ones aim to reduce the number of queries by leveraging also the substitute model, but still they require a large number of queries as the substitute model cannot be fully exploited. So considering the widespread use of commercial DNN services, this paper aims to propose a query-efficient adversarial attack. The challenges are twofold. First, how to exploit the transferability of adversarial perturbation to boost black box attack. And second, how to design an effective and query-efficient adversarial attack. Let's first look into the transferability of white box perturbation. We use adversarial regions to visually illustrate the process of adversarial attacks. An adversarial region denotes the area in the embedding space where the generated examples could deceive the model. And as shown in the picture, the light blue area denotes the adversarial region of the target model an attacker wants to compromise. And the transfer-based attacks generate a candidate adversarial example in the adversarial region of the substitute model. And this, since the substitute model and the target model could be different, so their adversarial region wouldn't be the same. So the transferability may not be ensured. So our intuition is to sample the variants of the original image in the embedding space through image augmentation. So we can generate multiple candidate adversarial examples. Just as shown in the picture, we can generate like three different augmented images from the original one, and two of the adversarial example generated from them could be fall into the overlap area of the target and the substitute models adversarial regions. So in this way, we can increase the likelihood of finding a sample that can successfully deceive the target model. To justify this intuition, we leverage FGSM, a known adversarial attack, to generate adversarial examples for 5 augmented images. compared with the original version of this attack. The attack equipped with our sampling approach, as shown in the right part of the picture, increases the average attack success rate by 9.6%, and while using only 2.1 average queries. So now here comes our proposed dispersed sampling attack, or the DSA attack. Our attack workflow involves image augmentation, perturbation constraint generation, substitute model selection, and also querying the target model. So first is the module of image augmentation. Based on the observation that varying the distribution or magnitude of the perturbation enables different transferability, we perform a white box attack on the augmented image. Meanwhile, we set a reasonable perturbation constraint and appropriate substitute models for white box attack to balance the magnitude and the transferability of perturbation, which we'll discuss in the following module. We have the perturbation constraint generation module as the second module. In this module, we dynamically sample constraints based on a truncated normal distribution, as this distribution can avoid selecting extreme values. And upon selecting a successful example, the upper bound is gradually adjusted to ensure continuous generation of smaller transferable perturbations. And also we have the third module, the substitute model selection module. We argue that the previous transfer-based studies, they only generate a candidate adversarial example in the intersection of adversarial region. But we claim that the union of adversarial region should be used to obtain white box perturbation. Additionally, we apply the roulette wheel algorithm to select the substitute model and dynamically adjust its probability of being selected during the attack. And overall, our DSA attack is an iterative process that continuously generates candidate adversarial examples in the embedding space. So first, we have generated an example and it fails, and also another fail, and finally, we have a successful one. And upon we finding this successful example, we would adjust this upper bound to employ a stricter constraint. So that's the process of the attack. And finally, when the difference is below a predefined threshold, we find the final adversarial example. We use public datasets and we evaluate DSA from 4 aspects. We mainly focus on the effectiveness and the query efficiency, the distinguishability, and the robustness. First, we conduct a closed set evaluation. We present experimental results on ImageNet here. The results illustrate that DSA can achieve the highest attack success rate and the lowest average number of queries, as shown here. And also, we plot the change curve of mean distance as the number of along the number of queries. We can see here as the query increases, the distance of each method decreases to different degrees. Compared with other methods, our attack, which is shown in the purple line, achieves the lowest distance on the own test cases while using the same number of queries. We used six defense methods to evaluate the performance of the adversarial attack. And the results indicate that the DSA can still exhibit the best performance in most tests. We also conduct open set evaluation. The open set scenario denotes that the attacker has no prior knowledge about the training data set of the target model. Specifically, we randomly select half of the images for each label and use them as one training set, and while the remaining images constitute the other set. The result demonstrates that DSA achieves the highest attack success rate and also lowest average number of queries in the open set scenario. It's a maximum increase by 21.7% in the success rate, and also a decrease by 86.1% in the average queries. We conduct a real evaluations for popular commercial DNN services. The results show that DSA has the ability to achieve about 90% average success rate within 200 queries. Compared with the second best result, DSA increases the success rate by up to 45% and reduces the average queries by up to 91.6%. Here we present the real adversarial examples of each attack against the commercial DNNs. We can intuitively observe that the adversarial example generated by our attack are mostly approximate to the original image. In contrast, the adversarial example generated by the others have noticeable features of the target image or the noises that are easily perceived by human eyes. So to conclude, we propose DSA, a decision-based black box attack. Our experiment demonstrated its superiority in effectiveness, query efficiency, indistinguishability, and robustness. Future works include improving the attack performance and under other distance norms, and also developing lightweight defenses. For more details, please refer to the paper and the source code, or thank you for your listening. That's it.